So, hi everybody. I hope you can see me behind this gigantic podium. I am a vertically challenged individual, so I will try to pop out from time to time. Again, my name is Mercedes. For those of you who don't know me in real life or on Twitter, I'm also known as the Crazy Chicken Lady because I own a farm and I raise chickens. So if you like tweets about chickens and servers and architecture, you should follow me on Twitter. So when I'm not doing that, I'm wrangling data and servers for Scripps Networks. And today I'm going to talk to you about my experience building a data pipeline with serverless architecture. So here's what I'm going to cover today. I'm going to give you a high-level overview of our existing data pipeline, or the old data pipeline at SLN. And it's going to go over the system architecture, what we learned from it, and what the requirements for building the new system are. Then I'll go a bit more in depth on serverless components we chose to build our new system. So we used API Gateway, which is a fully managed API service from AWS, Kinesis Streams, which is basically a big queuing system, or document store. Lambda is written in Python, and EMR, which is a managed Hadoop platform. Maybe my slides will advance correctly. Oh, no. So our use case, we're an online video syndication platform. We have about 2 to 3 million streams or events generated per day. Our data pipeline supports analytics reporting, video recommendations, and development and testing and ad targeting. So we have a lot of data needs. Some of this reporting is needed daily, while other insights are needed hourly or immediately. So what does real-time mean? A system is considered real-time if it ingests and processes individual events as soon as it receives them. Batching or holding events for later processing isn't real-time, even if the batches are frequent. So essentially, a real-time system has the ability to receive, process, and respond to a request or a piece of data on demand. Data can only go so fast over the wire, and more components in the system increase latency. So this is a big, ugly diagram of what our old data system looked like. It's actually not terrible, but there are some things that didn't work so great about it. But it supported about 100 million events per day. So websites host our video player, and we provide content and advertising. Behavioral data is generated when an event happens in the player, whether it be an ad impression, a video start, pause, et cetera. And that data is sent to us. The Edge, which is the Nginx web server on the very left-hand side, is basically just an Nginx web server that receives the events. It's a JSON payload and an HTTP post request. It then logs that to a file. That file is then rotated out and uploaded to S3 every hour. At the same time, data is sent to a socket, which is read by our syslog, and that forwards it to our real-time system, which is which is basically an ELK cluster, so it's Elasticsearch, Logstash, and Kibana. We don't do a lot of reporting on that, but that's what we use for like ad hoc analytics, and the developers use it to kind of look at the data as it comes in real time. So after the current hour's data from every web server is uploaded to S3, it's then ingested into Hadoop via an Uzi in a batch. And it takes about 30 to 45 minutes to process and do reporting based on that data. So it can take up to 2 hours from the time an event was generated to the time it actually updates a metric or a report. So what did we learn from this system? Besides, it was a little bit of a swamp of sadness in terms of maintaining it and giving us answers. It didn't always give us the correct information. So we would like to be able to run real-time continuous reporting, and we can't easily do that with this system, being that it's basically a batch. The ELK component wasn't as easy to transform our Hadoop queries into things that we could run on the Elasticsearch cluster, and it was just a little bit too much load for what we had, and we didn't have the bandwidth to scale that up. So we are looking at running real-time continuous reporting in a different manner. The other problem we ran into was scheduled jobs aren't always aware of the data source. So they might run, and the data might not be there, and they succeed, and they're like, great, we have reporting. And we look at it, and we're like, that doesn't look right. That's not accurate at all. And we're actually missing data, so that's great. relying on logging to disk as a means of data collection is really prone to failure. So we're thrashing disk I/O. We're thrashing disk I/O every time we receive an event. We're also thrashing it every time we're uploading and rotating that file out to S3 because we're making a copy of it. It's many gigs of data. So that was affecting latency in our system with Nginx. So we want to move away from that. We also have to do a lot of data cleanup. Nginx has a security feature that substitutes hex encoding for quotes in the JSON payload, which breaks the JSON. And we have to go back and parse and clean that up later. So there are a lot of steps to getting data in the right format and also getting it to the right place. And this kind of complex chain of events was costing us a lot of overhead in terms of maintenance and also engineering time to be able to develop new reporting based on this system. So what do we need to do to go serverless? Or really, what the question is what do we need for a new system? Our new system needs to allow for streaming analytics, and we need to reduce the system complexity. So any new system should reduce the number of services the data has to go through in order to reach its destination. And those services need to be independent of one another. So the old system was also running several services off one type of box, which was the Nginx web server, and then routing it to a chain of load balancers, Logstash, syslog, Elasticsearch, Kibana, et cetera, et cetera. So we would get latency delay in the system. Often we would get JVM out-of-memory issues from Elasticsearch, and that would cause a backup in the entire chain. Our biggest requirement is that we need to log data and store it in S3. That was kind of the easiest thing to build around, since it was going to be able to allow us to port what we had, and also it's a pretty solid design anyway, and it worked for us. So that was the one requirement that we had to port, was it had to store data in S3. So this is what we came up with. This is a bit simpler than our previous implementation. Instead of a bank of web servers, I'm using API Gateway for the request payload. So this is, instead of having a load balancer and Nginx, I just use API Gateway, and our JavaScript player does a post request to that. So that then feeds a Lambda that takes that data and puts it into Kinesis. So it basically just transforms a post to a put. Once that data is in a Kinesis stream, it tells another Lambda function every 100 events to process those events and store it into a file in S3. From there, we'll have several more Lambdas that are triggered in S3 events to do Redshift, Elasticsearch insertion, and our Uzi pipeline, which is left over from our Hadoop implementation, runs every hour on EMR now instead of Hadoop. So we were able to use all of the existing reporting jobs that we had. We just transferred it to a new system. So now I'm going to get to the meat of this presentation, the how and why of the serverless, how and why we went serverless using AWS offerings. So I'm going to get more into detail from the API Gateway to S3 portion of that previous diagram. So why API Gateway? We have video players embedded in pages that we don't own or control. And for ease in data collection and ability to secure credentials, we're not requiring the client to authenticate. You can, of course, do so if that's something you need to do. You can create an API using AWS Console GUI tools or by using Swagger. I haven't actually personally used it, but in doing research and automation tools, that was one of the ones that came up. And it looked like it was pretty straightforward and easy to use, and supports infrastructure automation. So if you have clients that can also authenticate using an IAM role or some other type of AWS authentication, you can also go straight to Kinesis, as it essentially just takes a put request. So you don't necessarily have to have an API in front of it. We just chose to do so we didn't have to make any changes in our player. Kinesis is basically a multi-subscriber scalable queuing system. So using an AWS client or authenticated HTTP request to send data to Kinesis, either one at a time or batching records by the put records command. So you can send multiple events at a time if you're using the Kinesis client library. It has 7-day data retention, which is a really nice buffer. So if you have something going on downstream and you can't resolve it right away, or if you want to do a new data source or do some new processing on top of that, and you want to pull from your history of Kinesis, you can pull from that 7-day window of data. Lambdas or other consumers can subscribe to the same screen, so it's multi-subscriber. And Kinesis will keep a transactional record for each to maintain the state of the data. This is kept track of in what's known as a shard iterator, and I'll explain shards momentarily. So each Kinesis shard is a unit of throughput, and what that means is there's 1,000 put records and 1 megabyte per second of throughput per shard of input. That was kind of a mouthful, I apologize. And 2 megabytes per second output. So when you put data into a Kinesis shard, you're able to draw it off faster, so you don't get delays and backups. So to increase the number of records that you can put into Kinesis, or the amount of data that you can put or pull off of Kinesis at one time, you increase the number of shards, and then to decrease that, you decrease the number of shards. S3, simple storage service. It stores file objects, and it's not a traditional file system. We've been using S3 as a central file storage repository for all of our important log files. So anything that gets processed through us generally makes its way through S3, unless it's from a third party that we don't necessarily control over. But then we can still put it in there if we choose to. It's inexpensive, it's very stable, and it's well supported. You can't interact with it in the way you would a traditional file system. You need to use a client library or the AWS command line interface to do that. Buckets are basically the directories. The keys are subdirectories, and file objects are basically the files. And EMR, which is we've been working on moving all of our data processing over to EMR from a 20-node Hortonworks Hadoop cluster. Instead of the scheduled hourly analytics jobs, we want to go the route of writing Lambdas that stream data constantly and then update reports as that data comes in. So moving towards an event-based real-time system. We can then choose to spin up the EMR cluster for daily batch processing, for doing other types of reporting that's more intensive, and for processing all of that data at once. So you don't have to have a cluster that's up and running. I don't have to maintain that. I just bring it up, do my processing, and then tear it down when I'm done. Hadoop has been a frequent source of operational troubleshooting and maintenance, and EMR is going to help us reduce the costs associated with that. So, what is AWS Lambda? It's a basically event-driven processing model. It's push-pull, so you can feed data to it, and as that data comes in, it does something with it, sends it to another Lambda. It can basically call another Lambda by pushing data to that, or any other type of system that operates on the same principle. Processing happens on demand as the data becomes available. More Lambdas will spin up as the number of events to be processed increases. It's essentially running on a very large herd of EC2 Amazon Linux instances, but you only pay for the time your functions run, and you don't need to worry about the underlying infrastructure. You can also do scheduled Lambdas for specific times and days or intervals, just like cron, and Lambdas can feed and trigger other Lambdas. So it's pretty flexible. It's a microservices-based architecture. So here's a basic Lambda function. All this does is take events and put them into Kinesis. And this isn't necessarily from API Gateway. This could be from anything that I choose to trigger it. Lambda is a compute platform, and this function is standard Python code. So that's kind of an important distinction, is that I can run this code anywhere. I just don't get to take advantage of the compute platform unless I use it with AWS. Boto 3 is the AWS official Python library, and it's included in the Python runtime for Lambda. So you don't have to worry about importing that. It's just there. I mean, you do have to import it into your code, but you don't have to worry about setting it up in the environment when you run it. And I'll get to that in a little bit. So the heart of every Lambda function is the event handler, which takes two arguments, an event and context. The event is the data that triggers the function, and the context is metadata about the function's runtime. So here's an example event, and it's a record or set of records. In this case, it's a dictionary. It contains metadata about the event itself, and then the data, in which case this is a base64 included string with the key data. Pretty straightforward. The type of record you will process will be different depending on the source. It can be a string. It could be some other type of event. A lot of times it's just either JSON or it's a dictionary in the case of Python. So when you're writing Lambdas, you should write them to only process one type of event. They're not going to process and be triggered by multiple different types of information. If you need another data source, you add another Lambda. So the context object has a few pieces of data about the Lambda function that are useful data points to add for logging or for getting more performance or debug data out of your functions. Remaining time is how long the Lambda has left to run, and the request ID is unique for every run, except in the case of a retry or failure, in which case it's the same. So Lambda is designed with scalable processing in mind. It's stateless. Data goes in from one source and leaves for another, potentially transformed, potentially the same, and just in a different data storage area. Previous data has no impact on the processing of current data. This is to allow Lambda to run as many copies of itself as is needed without clobbering records. If you're storing anything, such as file names in S3, make sure you use a unique identifier. If an exception is raised, the Lambda function will retry on that event data until it succeeds or until the record expires. So for Kinesis, that could be 7 days of retries. In practice, you should monitor your retries and failures. And if you're seeing a lot of them, or if you're seeing the same request ID or seeing the same repeated error, you should take a look at your Lambda, the type of data that's coming in, and the entire system to see where you can optimize that. So here's another example of a Lambda function. This is the one that loads our Kinesis data into S3. And this is what actually replaces 6 Nginx logging servers, a load balancer, and a cron job. So as an ops person, I love this because it's 50 lines of code, and I don't have to worry about the underlying infrastructure. So I would normally write out a series of events into a file, and then copy that file over to S3, and then clean up after myself when I'm done. However, I don't have access to disk here. So I have to take records from Kinesis in batches of 100. I can take that number and scale it up or down as needed. I'm concatenating that into a string and then compressing and coding it using bzip2. I'm then uploading that compressed string as a file to S3. And that function ends with logging the success or failure of that request. I'm using a small batch here because I want to process data quickly, and I want to optimize for memory and speed of execution. I can adjust that number up and down by monitoring how long my Lambda runs with the context object, and also by looking at logging, which I'll get to, and how much memory it uses. So logging and monitoring. Logs are visible in CloudWatch immediately after a Lambda function runs. This is where you'll get more information, and this is an example of the information that you'll see after your Lambda finishes running. The last line here kind of lists the actual duration of the function, the build duration, and the build and used memory footprint. So for example, here it took 308 milliseconds. So we're build in 100 millisecond increments that actually build us for 400. So I can optimize there by trying to get as close to 400 as possible with the number of records or the size of the records as I can without going over, so that I know I'm getting exactly what I'm paying for. Same thing with memory size. I set this as a 128 meg max memory, and it used 28. So this is kind of a, it's an over-provisioned function, but this is about the minimum provisioning that you can do with AWS. You can scale up memory, and you can scale up the maximum duration as you need to. So monitoring these numbers are how you're going to tune your function to get better performance and more effectively utilize memory and time. So, and you also get some nice basic metrics dashboards. These aren't super detailed or fine-grained, but it's good at a high-level overview. And again, if I failed to mention it, this is in the AWS console. So this is all just stuff you can click around and look at. The invocation count here is how many times the function has been called in a given period. The duration is, of course, runtime in milliseconds. An important note is there's a limit of 100 concurrent Lambda function executions per account. So if your Lambda functions pass this number, some will be throttled. And there's invocation errors, and throttled invocations are the graphs. I don't have any currently to show you, but that's where they would be if they showed up. So what this means is that if you have 5 Lambda functions, and each of them has to run 20 copies to process your data, any additional Lambdas that spin up to run won't run until one of those 100 currently running functions has finished. So testing this. Since our code can run standalone, I can run unit tests against it. I can test it with whatever testing environment I prefer. I think I use unit test 2. You'll need to mock out the event and the context object and any external dependencies. Well, you don't have to, but that's good practice to do so. You can also invoke the Lambda functions using AWS command line tools, so you can actually see how they operate in kind of real time. You can give it a payload and also run it as a dry run, so it doesn't run any of its effects. If you don't actually return anything in your function, none of my functions return any data once they run. They just dump files to a bucket. So I don't actually get any confirmation. It just finishes running. If it finishes without an error, I know it's good. So packaging. All of the built-in functions for Python, of course, as well as Boto 3, are included in the Python Lambda runtime. If you're using any external libraries, you'll need to add those libraries to a zip deployment package. So this is pretty straightforward and simple to do, just making sure that you're zipping your file directories recursively so you get the contents in addition to the directories. I totally missed that the first time around. That was entertaining. So you can either install the libraries directly into your project directory by doing pip install-t, and then zip the contents of that entire directory, or you can zip up your project file and then go to your site packages in your virtual env and zip up the contents of that directory. So basically, you just have to put all of the stuff you're using into the cloud, which is what we're trying to do anyway. So we just started adopting Travis CI, and it's great because we use a VPC, so a lot of the Travis stuff it's a third-party tool. It's outside of our VPC. It can't access it, but it can access deployment tools for Lambda because that doesn't run inside of a VPC necessarily. So what it does is it spins up a Docker container. I install some tooling via pip, and then I script some shell commands to do basically a update function code. It was a little too much to show in this slide, but there's some demonstrations on how to do this in the AWS documentation if you're curious. AWS command line is a Python package. It's pretty easy to use. Also, I haven't personally done this, but you can also use CloudFormation templates to deploy Lambda functions. We probably will go that route, although we use a packaging on top of that to do more composable infrastructure, which is another talk in and of itself, so I won't go into that here. It's also possible to upload the zip functions to S3 and then do the deploy from S3. So if you're doing particular versioning or staging and whatnot, you can trigger code deploy or Lambda functions from S3. So summary. This is Python 2.7 only, if I forgot to mention that. So no Python 3. If you are sad about that, I'm sorry. Vendors have to go with completely stable and tested technologies, which often means they are several versions behind. It's fantastic for prototyping something that we're not sure how it will prove out or what we need to do and need to get it working. We can spin up functions faster than we can servers. So this was pretty great for a lot of this work that I'm presenting here was pretty much done in a prototype, and we're in the process of putting it in production. but it took us took one person maybe like a few weeks of working on and off, working on other projects. So API Gateway ended up being prohibitively expensive for us to use as a long-term data ingestion endpoint. It wasn't really designed for that, especially with this cost structure in mind. So what we ended up going back to is just using those Nginx web servers, but making them as efficient as possible by pulling out all of the logging and only making it as a pass-through. So it's really just doing a proxy, which is efficient, and that will work for us in the long term, and it costs us several orders of magnitude less. So it makes sense to go serverless in some cases, but not in all cases. We have a small team and a small amount of resources, and we need to be strategic about how we allocate that time and cost. One other thing is vendor lock-in. So this kind of ties us to AWS. For us, that's not as much of a problem because everything else we have is bought into AWS. We're fully on the EC2 infrastructure. Everything we have runs on AWS, and we're not planning on changing that. But if you're considering this, think about how difficult it will be to move away from this if your needs change. So I'm going to stand on my soapbox, maybe out here. And why is an ops person advocating for serverless architecture? Serverless is a tool in your Swiss Army knife that you can pull out to solve problems. Going serverless will not solve all of your infrastructure problems. It just pushes them to a different part of your stack. If anything, going serverless will allow you to focus on your product and systems architecture in a more critical light. The server is now a black box that you don't own and you can't easily debug. It's helpful to have operations and systems-minded folks in your engineering team to help you design and build automated, repeatable, and scalable infrastructure. Serverless components are one part of that. So I hope I have intrigued you to learn more about serverless architecture and components. Here are some resources to get started. And these slides will be posted later on as well. The first two links are information about AWS and a couple other vendor serverless cloud offerings. We used AWS, but there are other vendors doing this as well. The third link is an AWS blog post about working with Kinesis. And the next two are documentation on AWS Lambda core components and limits. If you're thinking about trying this stuff out, read about the limits. That's going to give you a lot of information. If you already have an implementation in mind you want to move over to, this will give you an idea of if it's possible or not. And the last link is a library for mocking Boto 3 when testing. So thank you for listening. There was a lot of information in this talk. We might have time for, no, we're done on time for questions, so you can find me in the hallways. And also I'd like to mention, if you're looking for someone to solve infrastructure or data problems in your organization, also come talk to me as I'm looking for some new opportunities. So thank you.